Good morning. Welcome to the Statistics 101 panel. My name is Mariana Cruz, and I'm a graduate student in the GMU Forensic Science program, and I'm honored to introduce the following speaker. Dr. Dan Milliner provides oversight and direction for medical aspects of the American Society for Clinical Pathology's ASCP programs and policies related to ASCP's global healthcare initiatives. Dr. Milliner completed his MD at the University of Alabama School of Medicine in 2000. He led the team that built an anatomic pathology laboratory in Rwanda and Haiti for advanced cancer diagnostics. Before joining ASCP, Dr. Milliner spent 10 years at Harvard, where he taught pathology, microbiology, and infectious disease. Thank you.
That's just not even my bio anymore, but it's fine. Thank you. I'm currently an independent contractor with 9 contracts. I run a nonprofit in Geneva, and I work for about 6 companies, but that changed in the last 6 months. So sorry about that. No problem. So thanks so much. First of all, everybody raise your hand. I'm going to start a different way. Everybody put your hands up. Now put your hand down. Keep your hands up. Keep your hands up. Only put your hand down if you've never had a formal course in statistics. Okay, now only put your hand down if you don't currently have an advanced degree in statistics. Good, 1 person, right? Awesome. So this will be the right audience for this talk. So what I want to do is talk to you about statistics and how it impacts your daily lives and all the work that you do across all of the specialties that are represented, and how to not be afraid of them, and also when to know what to do when you have questions. So this is just a quick overview. I want to talk about what statistics are, what that means. We had Chris just use a bunch of statistics earlier. I'm going to explain what those were, not specifically his, but you'll understand exactly what he was talking about. And then really talk about the value of descriptive versus comparative. Largely, you are dealing with descriptive statistics in your daily life, but you may run across comparative statistics, especially in the courtroom as part of a trial. And then give you some really fun case examples that are meant to be light and airy and exciting, although they get a little dark, but that's okay. And then talk about the challenges and using and understanding statistics. And just for your information, I have a master's in epidemiology, and I wrote a book on statistics. So I know a lot more about this that I'm going to try to convey to you. And I hope that my skill at communicating is going to come through and you don't feel overburdened by this talk. So let's talk about the lay definition of statistics. And I apologize, I don't have my readers on, so I'm going to have to look back here a little bit. So the lay definition is any quantitative description of an event about which we attempt to infer or assume something, right? And Chris did that in his talk. He said 75% of people use their cell phone on their toilet, and that meant something to you. Like, oh, you know, that said something to you, even though it was just a statistic that he found and plucked out of the air. You had some inference about it. You thought it meant something to you, and he hoped it meant something to you. Sadler has a batting average of 450, so he's going to be trouble for Kinsey pitching today. So when we think about baseball statistics, when someone says that, which the talking heads say these kinds of things all the time, we think, oh yeah, he's going to be trouble. But is there any validity to that? Let's look at that in detail. But then there's the scientific definition. This is a little wordy, but it's the practice or science of collecting and analyzing numerical data, often in large quantities, doesn't have to be, especially for the purposes of inferring proportions or differences in a whole from those in a representative sample. It's very wordy, but here's a solid example. We sampled 1,000 people with diabetes and measured their cholesterol levels before and after 1 hour of exercise 3 times a week for 1 month, and found that exercise significantly reduced their cholesterol on average by 24%. Okay, so that's a bunch of stuff, but in there is true statistics that I'll show comparative statistics for you. So let's look at these in detail. So this is baseball. Sadler. Is Sadler going to be a problem for Kinsey? Well, it all depends on context. If Sadler's batting average is 450 against Kinsey, right? If only against Kinsey, then, you know, there's a 45% chance that he's going to do okay, but there's a 55% chance that Kinsey's going to do better than him. So even if it's only against Kinsey, the odds are not in his favor. Although we think with the batting average of 450, he's doing really well, but that's still not better than 50%, right? If this is just general batting average, then it doesn't mean anything with regard to this Kinsey person at bat. And that's the same thing for a trial. Even if the statistics say that your defendant, your victim, whoever, 95% chance that this is true, that doesn't mean it's true in that case, right? So you can't let statistics overly influence how you think about these things. But here's some actual statistics on batting averages, which are really interesting, right? This is descriptive statistics. There's no comparison here. We're not saying anybody's better than anyone else. All we're doing is collecting that data and showing it in a time-lapsed way. So if we look at the far left, you can see the average batting averages from before 1880 through 2000, and they're all over the place, right? What is the most important impact on that batting average? Things that have nothing to do with the batter and the pitcher. It's the rules of the game. It's the bats that they're using. It's the baseballs that they're using. It's whether or not they're playing at night, right? These have these massive effects. And you can see that the game was very unbalanced from 1880 till about 1980, right? It was very unbalanced. It was all over the place. But about 1980, we suddenly realized we have to have rules. The bats have to be the same. People can't be on steroids. Like all these things are really important. And suddenly our batting averages start getting flat, right? So if we look at the other two curves, this is a longer term, and you can see that batting averages are kind of dropping down, but they're pretty flat. And those black dots on the bottom right picture are the big hitters, the people over 300. So even though the average batting average is going down, the big hitters are still there. There's still people that can do better, and these are why they get paid millions and millions of dollars. But notice in 2020, the best batters over 300 are about average what all batters were in 1920. Okay, so that's a comparison. We can actually statistically test that and show that that's true. But just from the trend, you can also see that that's true. And in the upper, what you can see is that in most recent years, pitchers are doing better than batters, right? On average, batting averages are going down, okay? This is all descriptive, okay? You could use this. There was a murder trial involving a baseball bat. This might help you, but the take home is that this is just descriptive statistics and we can learn a lot from it, but it's not, there's no statistical rigor that's been done here. It's just collection of data and demonstration. Here's that other example. And I want to walk you through this just so you're very clear on what we mean by statistics. So we sampled 1,000 people. What does that mean? There are 30 million people with diabetes in the United States. We can't do a study of all 30 million people, so we have to sample them, right? And of those 30 million people, some of them are white, some of them are Black, some of them are women, some of them are men, some of them are Hispanic, some of them are Asian, some of them are disabled, some of them have HIV, et cetera, et cetera. So when we sample 1,000 people from everybody, if we account for that, if we say we sampled 1,000 people from the general population and our mixture of the people in our 1,000 sample looks like all the people that have diabetes, we can now generalize from our study to the whole population. If we only took 1,000 white people or 1,000 Hispanic people, we can now only generalize to white people or Hispanic people, right? So when you read a study and how it's designed, this becomes very important. This is one of the most common biases in almost all of scientific literature, is that something like 80-something% of all cancer studies are done on white people. And we have no data on how African Americans, how people of African ancestry, people of Middle Eastern ancestry, how they do with cancer data, because all of the studies are done in one race, right? So we have to, that sampling is very important. People with diabetes, okay? I can't look at you and say who has diabetes, right? I have to test you, or I have to ask you a question. I have to invade your personal medical history to know if you have diabetes. So we're doing something a little more invasive, right? We don't need to do that for batting averages. We can just watch them bat and write it down. But if we want to know about diabetes, we have to ask you questions. Then we're going to measure it. That's an intervention. I can't measure your cholesterol by looking at your cell phone, right? I actually have to stick a needle in you and take some blood in order to do that. And so it's more invasive than just just an observation. We're going to measure cholesterol levels, again, before and after 1 hour of exercise 3 times per week. Now, this is probably poor study design unless you have these people in like a camp where you can watch them every day, because guess what? They're probably not going to do that exercise. But if you trust them to do it, maybe follow their Fitbit data, their cell phone data to know that they actually did the exercise, you can then say, after a month, what did we find? Well, before our study, was 235 milligrams per deciliter plus or minus 15. That's the average or mean plus or minus the standard deviation. And after the study, it was 179 plus or minus 15, okay? I don't need to explain statistics for you to know that it went down, right? All of you are like, oh, it went down. And most of you would probably guess that it was statistically significant, even though I've told you that. But why is it statistically significant? Well, all of that aside, this is where the statistics comes in. We compare those two means to each other and the standard deviation using a t-test of paired means, because it's the same person on both sides. And we get a p-value, which you've heard of many times. And that p-value is the probability that we would find this by random. And the probability p-test for this is like 0.00001, which means that there's a 0.01% chance that randomly these people have that difference in their cholesterol. So no, it's not. It's truly a difference and their cholesterol has gone down. So that's statistics. And when someone is using a study or quoting a study or trying to use that as part of their case or their data or their evidence, et cetera, all of these things matter for the context. And I'll show you that a little bit in a little bit more detail. So let's talk in detail about descriptive statistics, right? I showed you some examples, but let's look at them. See, these are brief informational coefficients that summarize a given data set, right? So what does that mean? So we're not saying there's a group of people here. What could we know about you? We could know what percentage of you were men and women, what your average age was and your standard deviation, right? How many of you drive a car versus a truck? These are all things we could gather about you. And those are just descriptive statistics. And we would summarize those by using means of central tendency or variability, things around variability, right? So your age, an average of your age, I would guess is probably 46 in this room. And the standard deviation is probably about plus or minus 15, because there are some of you that are quite young and some of you that are a little bit older, right? So I just made that up, but let's just assume that's correct. Then there's also the median. What's the median? That's the number in the middle. The number in the middle, if it's a normal distribution, meaning you're equally distributed across all ages, would be the same as the average. But I don't think that's true. I actually think most of you are older and some of you are younger. And so we have a skewed population where we see skewness. So the median is probably higher than the mean, right? Because it's of the way the average is working. So these are all just descriptions that are there. So here's some examples. The mean age of the class is 45, as I said. The median income is 34,500. You hear that all the time, the median income. Why don't we report the average income when we talk about incomes usually? Because they're grossly, egregiously different, right? There are people that make massively too much money, and there are people that make no money. So we talk about medians because we're trying to kind of balance it out and make it not sound so bad, but also because the data set isn't normal, right? There are way too many people that make only a little bit of money and a few people that make a lot of money. So it's not a normal distribution, it's a skewed distribution, okay? The standard deviation for the gap between junctions is plus or minus 0.5 inches. If you've done electrical work or built a house, you know, there's standards and codes about how you put studs up or put electrical boxes up, and you have to be within a certain range. And that's a standard deviation that you have to apply to, and you can compare that to a benchmark. And I already explained skewness, but let me explain kurtosis. So let's say the average age in the class was 45, and everyone in the room was either 43, 44, or 45, or 46, right? That would be a very peaked distribution. Like everybody be around a same mean. There wouldn't be anybody on the outside of that. So that's a very peaked curve. Whereas let's say the average was 45, but we had some 5-year-olds and we had some 85-year-olds, and they were kind of peppered all through, we would have a very flat curve. Like we would have a mean, but it wouldn't mean anything because everybody was distributed across it. So kurtosis is that, is it a flat process or is it a very peaked process? And those are all just, again, descriptive statistics, but they help us understand what data looks like and decide how we can analyze it, all right? Okay, so let's take a good example. Or sorry, let's look at, we'll look at an example in a second. So descriptive statistics are useful when you have a group of items like people, accounts, or cars that you want to provide a summary of, right? You've got a big group of data. You want to make sure that your audience can understand it. So you use these descriptions to describe it, right? The benefit, it allows for a simplified version of a complex system when trying to explain or make a point, okay? If the average age of everyone in a classroom is 45 and we have someone who's 20, we can say that person was an outlier, right? If the average age is 45 and the person is 45, we can say, well, they're the average age of everyone in class. So it just helps us summarize that. The risk, however, is that the assumptions about the groups of items must be true for the description to be of value or to be valuable. What does that mean? So if I'm giving you a mean or an average of a group and it's not normally distributed, if it's a skewed population, that average doesn't mean anything to you. Really, we should be talking about the median, for example, the number in the middle, not necessarily the average. So it's very important to understand that data when you describe it. So let's look at an example. Here's a parking lot. Okay. And everybody can like look at that and pretty quickly, what's the most common color car? White. White, right. So we can count, there are 143 cars and 80 of those cars are white. So white is, we could say white is a popular color. 55%, more than half of the cars are white. About 25% of the cars are darker or black, dark blue, black, whatever. We can see that. There are about 10% of the cars are red and only 1% of the cars are yellow. So can we, that's a description, and I've summarized that for you. Can we make any inferences about that? White is a popular color. Yellow is not a popular color, right? I mean, that's probably about the best we could do. But what if this is the parking lot for a delivery company that uses white cars to deliver their stuff? Well, then our data is skewed because their white cars are here because it's represented by some context that we didn't know about. Or if you're in Southern California, this would be probably every parking lot because it's so hot there, we all drive white cars, right? And so that's, you maybe say, oh, this picture was taken from somewhere in the Southwest because everybody has a white car. But we don't know any of that to be true. All we can say is that 55% of these cars are white, 2% of these cars are yellow, and that's about it, right? It's descriptive statistics. Okay, so these are applicable to the group in question, but they can only be used to make generalizations about a member of the group, and they may not be applicable to a non-member, right? This is really important. They're crucial for determining what type of tests can be performed on that or for another group, okay? So let's look at an example. Mr. Smith lives in the neighborhood between K and N streets from 1100 to 1400 blocks. The average income for residents in this neighborhood is $32,259 plus or minus $4,200. So is it true that Mr. Smith's income is $32,259? Maybe, but we don't know that that's true. That's not a true statement. What is true is there's a 95% chance that Mr. Smith's income is between 23,000 and 40,000. We know that's true, right? We can state that with confidence, right? So when someone is presenting to you, well, the average income is this, so this person had this much income. No, this is the probability that he had that income, right? You just have to understand how to state what you're using the statistics for to make sure that it's clear. Here's another example. The average price for a home in Cotton, Iowa is $235,000 plus or minus $35,000 for a 3-bedroom, 2-bath home. The average price for a home in Selda, California is $435,000 plus or minus $54,000 for a 3-bedroom, 2-bath home. And if we want to ask the question, are these home prices different? I mean, they are different, but is it statistically different? We now can see that they have a mean. They look to be normally distributed because they have a variance that's not that far apart. So we can actually perform a t-test of means to show that Selda is significantly more expensive than Cotton, right? And that's valid. When you look at that data, you can say from the descriptive statistics, I could use that test and it would be okay. But then look at the data here. The average price for Cotton, Iowa is $235,000 plus or minus $12,000. The average price for a home in Selda is $435,000 plus or minus $420,000. That doesn't make any sense, right? So the Cotton, Iowa has that peaked kurtosis. That's what that data looks like. And the average in Selda is a skewed population, right? Clearly, there are lots and lots of very expensive homes because it's got this weird average and standard deviation. So we can't use a t-test of means to do that. Just from the descriptive statistics, we know exactly what kind of test we could use, which is actually a Wilcoxon-Rank sum. And I'm sorry for those of you who are cringing from hearing a Wilcoxon-Rank sum, but that's the test we can use to compare them, right? So this concept of descriptive statistics or understanding them is crucial for making these comparisons. And you can't let someone try to do a comparison or throw some statistics at you when this kind of situation happens, when they're using the wrong background data, and it happens all the time. So here's a whole bunch, I hope you can see these. Here's a whole bunch of descriptive statistics. I just want to show you some examples. So at the top left, you have bullets with their cartridge size, the type, their feet per second, the energy, the power, et cetera. This is all descriptive. Now you might use this in the lab to compare it to some data to see the velocity from a video or something like that, but it's just a bunch of data that's all summarized for those cartridges. Does every single cartridge fire at 2,719 feet per second for a 22 Hornet? No, there's a standard deviation, there's an average, but that's just summarized as one number, but you know in the back of your head that there is some variation there, right? At the top left, you see some lab data. We have some typical chemistries. You have the average for a population, you have the standard deviation, you have the coefficient of variation. That doesn't mean that a patient's lab test has to be within that range to be normal or abnormal. That's just the average for that particular test, right? Based on the reference range that's given there. Here you have 48% of adults find it acceptable for DNA testing companies to share users' genetic data with law enforcement. That means 52% don't, right? But look at the variability. There are variations in age, there are variations by men and women, variations by income, et cetera. And so if someone is arguing with you about whether or not you should do that, and they're talking about 18-year-olds and you're talking about 50-year-olds, it's a different population. They have a different opinion about that, and those descriptions are there. This is a really interesting one. These are stab wounds by age, a little bit of forensic pathology for you. And you can see that they're less than 25 and older than 25. They have the same basic locations of the stab wounds, and then they have percentages. And you can see there's variation in the red and blue bars. This table is descriptive statistics. It's describing what you find in that population. And only where you see those little bars with the little asterisks, which you can see here, have they actually done statistics, where they've actually compared those two to see if they're different. Everything else in this whole table is just a description of the data. And those are actually the statistics. And you can see that in, I think, 5 out of the 8 examples, there's a difference in how people stab depending on how old you are, which I think is fascinating. Okay, so now there's comparative statistics, right? And this is the least important for you, so I'm going to go through it pretty quickly, but I just wanted to make sure that we've covered it. So this is the comparison of groups of samples to identify differences or similarities. It's very straightforward. All of it depends on those descriptive statistics I just described for you, but this is the differences between them. It typically uses a descriptive statistic from each group and then formally compares them using a statistical test. And these are the things you hear all the time. Group A is 5 times more likely to buy Group B to buy Tide detergent, right? Dentists approve, like whatever. Families in Alabama make $20,000 less per year on average than families in California. I'm from Alabama. I now live in California. I know that that's true, so I made that up. But you know, that's what you hear. Someone did a test to show that that was true. This is a good one. Dr. Smith and Dr. Jones are highly correlated on their reads of tissue slides from this study, right? So this is really relevant to what you do, because often in a civil trial, sometimes in a criminal trial, you'll have one pathologist on one side that reads a slide and another pathologist on another side that reads a slide, and they'll have completely different opinions about what they see on those slides, right? And is that common? Do pathologists often disagree on what they see on histology? Isn't it a very objective specialty where when you look through the microscope, what you see is what you see? Absolutely not. You can ask 20 pathologists to look at the same slide and you'll get 20 different answers, right? They're almost all the same kind of answer, but they're very, very different answers. So this concept of Dr. Smith and Dr. Jones having highly correlated reads means that they're probably in agreement, and is really helpful for what you're trying to do. Okay, now comparative statistics are very complicated, and I'm going to show you that on the next slide. But for this, I just want to give you a flavor. So the types of tests the type of test you can do depends on the number of groups, right? Do you have 2 groups? Do you have 3 groups? Do you have more than 3 groups? The number of items. Do you have only a few things you're comparing? Or are you comparing a lot of things? And the type of data, right? I'm not going to go to this, but categorical is like girl, boy. Continuous is 1, 2, 3, 4, 5, 6. Binary is yes, no, right? That's the very simple way to think about it. And the description of the data set. So here we go. We compare 4 groups of patients with and without diabetes who receive a medication and a placebo. So there we have 4 groups, right? They either have diabetes or they don't. And they either receive the medication or they don't. And we want to compare the numbers between those, okay? And you can see an example of what that data would look like. We compared the shotgun pellet distribution from 3 brands of shells in 4 different shotguns, right? So we've got 12 different conditions there, and we want to look at comparisons. We asked people categories by age, gender, and ethnic identity to rate our cola versus another cola on a scale of 1 to 10. All of these things are measurable. You can quantify them. You can come up with a number, but the test that you use is important. And this next slide is going to give you a headache. These are all of the statistical tests that you can do. Okay, I don't expect you to know what these are. I know what all of these are. I know how to use all of these. If you need someone to do that, you can always call me and I can help you. But the point is that this is the complexity of how to do those tests. And how often do you think in published peer-reviewed scientific literature, how often do you think those scientists use the correct test for the data that they're doing? It's not as often as you think. It's sometimes, depending on the journal, it can be up to 25%, sometimes up to 35% of the stats are wrong that they used. Okay, this is why it used to be much worse. It's getting better, but this is why statistical rigor, statistical reviews have to happen now. NIH grants often require statistical review before you apply for them, because people they pick the wrong test. So let me give you a really important caveat to this, which is effect size versus significance. So the value of 2 comparative statistics are 2 parts, right? There's the effect size, which is the difference, 235 milligrams versus 175 milligrams of cholesterol, right? That was the effect size. And then there's the significance, right? The probability of seeing the difference by chance. We know, because I told you the 235 versus 179 is a very, very, very low probability that you would have seen that by chance. So it's not by chance. This is a true difference, right? That's how we imply that. But there's some important caveats. Given a large enough sample size, this is very important. Given a large enough sample size, all effect sizes can be shown to be significant. Okay, I'll give you an example of that in a second. Regardless of the significance level, an impractical effect size does not matter. Okay, that's the same thing stated a different way. If an effect size is large enough, significance is an eventuality, right? So that 235 versus 179, that's a pretty big difference. Even if we didn't get statistical significance with 1,000 people, we probably would with 1,200 people, right? It's very little needed to get to significance. And then an effect size, if an effect size is so small as to be impractical, seeking significance is irrelevant. Okay. Now, why is this a problem? This has plagued my life for the last 6 years. For those of you who know anything about cancer, immuno-oncology is the new treatment for cancer. Pembrolizumab is all Keytruda. You see it all the time on the television. Keytruda. Keytruda is like a wonder drug. It kind of treats 50 different kinds of cancer. It's really amazing. But there are a whole bunch of other drugs like Keytruda that were all approved within about a 3-month period. And we won't get into that because it's quite political. And I know we have a mixed audience, but that approval was trying to drive down the price, not because we needed those drugs. And then the data for those drugs versus Pembro, the difference for patients was tiny, but it was significant, right? And that was enough for the FDA to approve these drugs. Long story, you can look into it, but the take home is it didn't work. All those drugs are still too expensive. But the point is the differences between those patient groups was not really what we traditionally would say is significant enough effect size to make a difference. So let me show you 2 extreme examples. So we observed one bowling ball versus one air-filled balloon in water and noted that the bowling ball sank and the air-filled balloon floated. Now, do we need to do statistics to understand why that happened? No, the bowling ball is super dense. The balloon is super light. If you do density, the densities are different, and that's what's guiding them to do different. We don't need to have more than 2 samples to do that, but we also don't need to do statistics on it to understand the difference, right? However, we recruited 150,000 participants, half of which took our medication. The other half took the competition's medication. Those taking our medication had an average cholesterol that was 1 point lower than the other group. Does that matter? That's 179 plus or minus 15 versus 178 plus or minus 15. Do you think that makes a difference to the average patient? No, that's an irrelevant effect size, but they found significance because they had enough people. Okay. And so don't let that make you think that that's an important study. That's a stupid study. That was a waste of money. There was no point in doing that, right? But they did it, just like the bowling ball and the air balloon. Okay, so let's look at some cases. I'm done with the boring part. So let's do some fun cases that are all hopefully relevant to what we're doing. So this is a laboratory test for substances. So Ms. Smith was arrested for driving under the influence, and a blood sample was drawn at the jail cell within 1 hour of being pulled over. She weighed 200 pounds and reported that she'd had a bunch of drinks with her ladies. Her blood alcohol level was 0.05 using the blood sample drawn 1 hour after her arrest. Okay, so you can look at this chart. You can see the pink area. It's a chart for women. So someone being very gender conflicted decided to make it pink for women. And you can see that at 200 pounds at 0.05, she is possibly going to suffer from criminal charges. Okay, during the trial, the defense calls the laboratory manager to the stand and asks him to explain the sensitivity, specificity, and accuracy of the blood alcohol assay. He says the test is highly sensitive and specific with an accuracy that ranges, very important, from minus 0.18 for higher concentrations to plus 13% for lower concentrations. Well, the defense attorney immediately jumps on this and argues that Mrs. Smith's blood alcohol level was much lower than 0.05 because there's a 13% increase in her measured level on the actual levels. He argues 0.44 and he refers to the chart at the right saying, no, there's no way she was actually intoxicated. So how do you respond to that? Well, you don't let the person argue what's not true. Like that's actually not true. So what are the biological statistical counter arguments? First of all, 1 hour had elapsed with Ms. Smith had not seen to consume any additional alcohol. So her alcohol level was higher when she was pulled over, and the biological natural degradation is about 0.015 per hour. So her blood alcohol, based on what was measured, was 0.065. So she was definitely in the range. However, though the test may increase it by 13%, that would result in a value of 0.44 plus the 0.015, which makes it 0.059, which still puts her in the pink level. Okay, so you just have to be confident with your ability and your technical person's ability to interpret it. And this is an easy one. I'm sure you all do this like clockwork. If you're in the courtroom, no problem documenting this. It's really easy, but I just want to give you an example of how someone can try to trip you up by using the natural state of the test. We can't change that 13%. That's just a product of the test, but we can make sure that our data documents what's happening with that case. Okay, this one is a little bit tough and it's going to get a little dark, but hopefully you'll be okay. So this is statistical inference, making an educated guess based on existing data, right? So Mr. Miller is a 34-year-old cis male construction worker, about 20% body area covered in tattoos, was driving a pink Subaru Outback when he was pulled over for excessive speeding. Now, without reading any of the rest of that, what is your brain saying? That's not his car. Why is he driving a pink Subaru, right? It's a little worrisome, okay? Now, these are all hypothetical, but just run with it, okay? National Registry records show that 43% of Subaru owners are women, and the vast majority, greater than 90% of non-commercial pink cars on the road are driven by women. National Registry records also show that men between the ages of 24 and 38 who work in physical labor, most likely 85% drive a pickup truck or similar vehicle. And individuals with more than 10% of their body tattooed are highly likely, 93%, to drive a pickup truck or an SUV. Now, I made those up. It doesn't matter. The point is, if you are a statistical savant, or you had AI, or you're just like an average citizen, this might be where your brain kind of falls, right? But what does the math say? So the math says 43%, 90%, 38% of pink Subarus are driven by women, and 6% of pink Subarus are driven by men. So there's a lower probability that this is his car versus it's someone else's car. But also there's like a 79% chance that he should be buying a pickup truck. Now, is that enough for you to incriminate him, search his vehicle, do something to him? Well, that's your problem in court to figure out, right? But stay with me here. This is where racial profiling comes from, right? This is the statistical basis of racial profiling. This is why this happens. It's not good. It's not, you don't want to, validate someone's rights because you have a gut feeling about something, but the statistics aren't on your side, right? There's a probability he could drive a pink Subaru. It's not out of the question. It's not impossible for him to do that. So you have to be very cautious to do that. Now let's take this case and look at it a different way. Mr. Miller is a 34-year-old cis male, straight construction worker, that doesn't really matter, who weighs 215 pounds, 6'1", has blonde hair, green eyes, dark tan skin, about 20% body area and tattoos, was driving a pink Subaru when he was pulled over for excessive speeding. The car smelled strongly of marijuana and cigarettes, but no contraband of any kind was found on Mr. Miller or in the car. Although the car was not registered as stolen, it was not registered to Mr. Miller and instead was registered to Mrs. Davis, a 26-year-old whose address is a few miles away. When questioned, Mr. Miller says Miss Davis is his sister and she let him borrow the car to run some errands. Miss Davis cannot be reached by telephone. Think about Chris's talk. Is that likely that she couldn't be reached by telephone? The trunk of the car contains a shovel, which has fresh dirt on it. Mr. Miller's boots are very dirty with fresh dirt, and he appears to have been heavily sweating recently and had dirt on his hands and forearms. We don't need any statistics to know something's up with Mr. Miller. Like something's going on here. We should investigate further. We don't know what it is. Maybe he's done nothing wrong. Maybe his errands were putting in a tree, but we really probably need to talk to Miss Davis before we just let him go with this car, especially considering this possibility of marijuana. So here, we don't need any statistics. There's enough evidence that we're worried about something going on that we want to investigate further, but there's no racial profiling. There's no, this guy could be doing something wrong because he's a construction worker with tattoos. None of that. It's like the evidence in the case is suggestive that something could be going wrong. So you want to be careful, right? So you just have to distinguish between when you have enough evidence and suggestion that something might be wrong, that you need to check this guy out, versus going with your gut, which could be even influenced by statistics that are not in your favor. Okay. All right. And this is like the fun case. So this is lots of percentages coming at you. Just bear with me. So there's a genetic DNA match against a national database. We heard about this yesterday for a sample from a murder crime in Pellington, Wisconsin. I made up all these places too. That showed a 50% somatic match, a 0% mitochondrial match, and a 100% Y chromosomal match to Mr. Davis, no relation to Mrs. Davis from the last case, a school teacher in Pellington who has 4 uncles on his father's side, 4 brothers himself, and 3 boys who are aged 17 to 24. Mr. Davis is questioned about the murder, and he has a solid corroborated alibi, which includes 2 of his 3 sons. They were golfing out of town. Mr. Davis' father passed away several years ago, and his 3 uncles live in different states. The closest is about 45 miles away in Minnesota. One of Mr. Davis's brothers has a prior arrest for aggravated assault, and another brother has discharged from the Army after a brief jail stay for conduct unbecoming. He beat another private almost to death. According to the laboratory performing the genetic test, the classification accuracy is 96.5% for recovered DNA versus blood sequencing. Further, the database for which Mr. Davis's DNA was recovered uses whole exome sequencing, which accounts for only 1% of the human genome, as well as selected YSNP sequencing and mitochondrial sampling. 63.8% of violent offenders recidivate by being arrested for a new crime or violation of supervision conditions. So who are the viable suspects in this case? Now, there's two ways you can look at this case. You can be like, well, his brothers are criminal. You know, that's not the right way to look at it because we have data. So we want to look at the data first, and maybe it is his brothers, but we want to look at the data first. But we have some genetic data. So let's look at that genetic data. So here is his pedigree, right? So this is forensic genealogy. This is what you guys have been doing. And Bodie is out there. I'm not endorsing or anything. I told him to come listen to my talk and tell me what I was doing wrong, which is fine. But you have, you have the father with his three brothers. You have the guy, the index case, which is this one. Let me see if I can do an arrow. No, I can't do it. The index case is the last in the middle on the right with his wife. And then you have his three sons. Now I said he had four brothers, so I'm actually missing one block. Sorry about that. There should be 5 people here. But here we go. So what do we know about the genetic data? Well, we know that he shares a Y chromosome with the murder suspect, right? Every male in this tree has the same Y chromosome, right? Because Y chromosomes come from your father. They all have the same father going down the line. So they all have same Y chromosome. So that doesn't help you at all, except that it could be someone in this family, but you don't know who it is. Mitochondrially, his uncle's mitochondria come from his great-grandmother. He doesn't share mitochondria with him. Sorry, wrong way. His mitochondria come from his mother, so he shares mitochondria with his brothers. And then his children have his wife's mitochondria, so he doesn't share mitochondria with children. Remember, he was a 0% mitochondrial match. So we've eliminated his brothers just from the mitochondrial DNA. Can't be any of his brothers, even though they have criminal records. It can't be any of them, but clearly crime runs in this family. Oh, did I miss? Oh, yeah. So who are the suspects? It has to be one of his uncles or one of his children, and only one of the children doesn't have an alibi, and one of the uncles is only 45 miles away. So just by thinking about it from that point of view, we certainly want to investigate all of them for all the uncles' point of view and the children, but we can eliminate the brothers that are in the middle. So again, with forensic genealogy, which is much more advanced than this is just diagrams. There's also numbers and those things that do that. It's important to look at the data and try to figure out exactly what's going on, because as I showed you, only 48% of Americans in general think that their DNA should be shared. And so on average, 52% of the time when you have somebody come in like this, they're not going to be happy about it, right? That you're looking at this or doing this. But if you can work with them in a way that makes them confident that what you're doing isn't incriminating them, but rather is sort of helping you figure out a crime, then maybe they'll be more supportive of what you're doing. Okay, this is the last case. So after an examination of a laboratory director on their methods for analyzing the blood, semen, and saliva evidence from a rape case, the defense stands to cross-examine the witness as follows. Mrs. Ganoche, isn't it true that every 20 lab tests you perform is likely wrong? Isn't it true that genetic analysis that incriminates a suspect usually leads to a confession, which my client has not given? Isn't it true that laboratories routinely misinterpret even the most basic samples? And he quotes several sources quickly for the basis of his questions and waits for an answer. And I'll show you those references in just a second. How many of you have ever had this happen to you, where someone, really aggressively attacks a witness with a bunch of statistical data, right? It happens. I've had it happen. It happens. Okay, so what are these sources? So here's his sources. Probability 1 blood test out of 20 with a 95% accuracy is wrong. This is a known fact in the laboratory. But what is the context? The context is if you take one person and you perform 20 lab tests on them, one of them will likely be out of the reference range. It doesn't mean the test is wrong, right? It just means it's outside the reference range. So this is a gross misinterpretation of that information, right? So if you know this data, if you have someone who's a lab expert, they can easily debunk that and say, no, that's not what that means at all. The false promise of DNA testing. So this was in a report. William Thompson, an attorney, said a criminologist professor at University of California told KJ, a reporter, it appeared that Houston police technicians were routinely misinterpreting even the most basic samples. Well, Houston police technicians are not laboratory professionals. The person on the stage in this trial is a laboratory person that's running a lab. And so it's just not the same context. You have to say, this is out of context. How do we, it's not the same comparison that you can do. And then here is, from the start of the book, the book notes that 10,000 or so DNA tests requested each year, between 25 and 30% end up excluding the prime suspect. In other cases, a positive result is usually followed by a guilty plea. So that's where that comes from. Okay. The problem is the lawyer knows that. So he's encouraged his client not to give a guilty plea because he's going to use this to argue that he's not guilty because he didn't confess, right? I mean, that's a circular argument. So what do you need to do? So if you, as I said, if you perform 20 lab tests on one person, one of them has a high chance of being outside the reference range. That's not wrong. That's just outside the reference range. You just quote that. The circular argument, the defense told him not to plea bargain because he's arguing the fact that if he were guilty, he would have plea bargained, right? And then technicians in the early 2000s had trouble with mixed sample analysis. That reference was 20 years old. And now there are techniques that allow even Houston technicians not to make that mistake because they have the right context. So all of this is all about the context of the study, how they're using it, how old it is, and how they interpret it. And having the right person on the stand, i.e. Marissa Tomei, for example, from our last case, is the way that you get around that. So lastly, I just want to talk about some challenges in statistics. So their context and assumptions are very important. Any use of statistics requires defining the context and the assumptions. This is not true. This isn't like in the academic world when we're writing paper. This is always true. You can't state a statistic, as we did with the baseball. You can't state a statistic without understanding the context and the assumptions about that. If you take a piece of data out of context, it completely eliminates its meaning. That's what the last defense attorney was trying to do, was take all those out of context and make them mean something, but they don't mean anything because they're out of context. And then using data about which assumptions are not met eliminates the meaning, right? So there are assumptions about statistical data, descriptive or comparative. And if those assumptions aren't true, it's not relevant to what you're discussing. So here's an example. We surveyed 1,000 Hispanic people in Mary, Arizona about their attitude towards gun control and found that 75% of them were in favor of less stringent, more open gun policies. So someone might say Hispanics in Southern California are in favor of gun control. Well, that's not true because this was 1,000 Hispanic people in Mary, Arizona. What is Mary, Arizona? Is it ridden with gang violence? Is it a massively Catholic community? We don't know. Without context of what Mary, Arizona is and who those Hispanic people were that we surveyed, we can't make any extrapolation about the rest of Southern California, right? So that's just a gross misinterpretation or gross assumption problem. Here's another one, classic problem, happens all the time. We show in a Cox proportional hazards model that the Black teens are more likely to reoffend over time than white teens from inner cities. What are those two lines doing? They're crossing, okay? In a Cox proportional hazards model, the lines can't cross. If they cross, it's a statistically invalid model. If you know that, then when someone shows it to you, you're like, no, that's wrong. That data is completely invalid because they're crossing. Now, there are tests you can do when they cross, but they've done the wrong one. And so that's where having someone understand statistics and data can help you figure out if somebody is just, BSing you or knows what they're talking about. Okay, misinterpretation, slightly different. Statistics and numbers are difficult to discuss quickly without a full understanding of the context. Thus, they are frequently misinterpreted when they are requoted. Context errors refer to making statements about which the data has no evidence, right? So misinterpretation is not understanding the primary evidence. This is the difference, right? Context I just showed you. Misinterpretation, they just don't understand it. For example, 89% of people with lung cancer were smokers. The misinterpretation, everyone who smokes gets lung cancer. Is that true? No, only 10% of people who smoke get lung cancer, which is a weird thing to think about. But if you wrap your head around it, 89% of people who smoke lung cancer, who were smokers get lung cancer is a small number. The number of total smokers is huge. So when we say 10% of people who smoke get lung cancer, now that can account for that large number of people with cancer. This is one of the most misquoted statistics, which is the reason I used it, but you can understand how that can easily happen. Here's another example. Gun control is curbing gun deaths in the United States. So someone says, gun control is curbing gun deaths. And you're like, look, in 2022, it dropped, okay? Well, if you read up at the top, it says gun deaths excluding suicides. And actually during the same time period, this excludes suicides. And during the same time period, suicides were actually the highest since 1993. So gun deaths actually had increased during this period, right? Because of suicides, but they're not accounting for that. So someone can, use the data however they want to try to make that difference, but they have to be careful about what they say. You can say gun control is curbing homicide-related gun deaths. That would be a fair statement, but it's not curbing suicide-related ones. And so gun deaths in general are going up. So the context really matters. Okay, I'm not going to go through these in detail. These are problems with source data. So someone throws a paper at you and says, I'm going to use this in trial, blah, 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 blah. And you look at it and be like, I have no idea what this is talking about. These are the kinds of problems you could find in a paper. I don't need to go through them in detail, but these are all the kinds of things we see in the literature. People write papers and they're wrong, right? They've done the statistics wrong. They've done their conclusions are wrong, all these different things. And these are all the things you can do. And how do you solve that problem? You need to have a biostatistician or a statistician look at that paper for you, right? And that's where I would strongly encourage you to think about, if you have something that you're worried about, just try to find a local university that has a stats program. Someone can read through a paper and give you in 5 minutes a summary of it and tell you what you need to know about it. So many journals produce terrible articles that are of no value because the statistics are done incorrectly. I wish that weren't true, but it is. These articles have passed peer review, but that doesn't mean they aren't garbage. And in my journal club, when I was in residency, we used to look at New England Journal of Medicine articles all the time, like the New England Journal of Medicine. And every fourth article we look at, the stats were wrong. They're just wrong. They just weren't done correctly. So only a trained scientist in statistics can review and determine if the results are valid. So consult with a statistician or an epidemiologist. They can review the data and provide you an accurate lay interpretation so you are prepared when someone tries to bring that up against you. Okay, so to summarize statistics, there's variable meanings, there's the scientific rigor, the causal usage, and data versus differences we talked about. Descriptive statistics is a summary of a group of items. They do not connote differences, prediction, or inference. You can't say anything, it's just a description, but they are useful for explaining a data set. Comparative statistics are measurements of difference, the significance of that difference, and they allow for inference about others outside test groups if they are generalizable, right? And then utilization, numbers are confusing, very easily misinterpreted accidentally or deliberately. And so you must have a defined set of assumptions and limitations when you're stating a statistic so that it's clear and accurate for what you're talking about in context, and you're not confusing your audience when you do that. And so lastly, just to show you statistical variation, this is my email address. This is me from early in residency through now. And I just think it's fun because I'm like thin, fat. And then really fun, if you don't know her, Rebecca Folkerth is that little face in the background. That was us in Rwanda opening a laboratory. And she was the neuropathologist for the Medical Examiner of New York for many years. And she's a very close friend. So that was the only forensic picture I had to show you. So anyway, thank you.